Hello and welcome. We're going to start our discussion of biology, interestingly enough, with a discussion of chemistry. And so we're going to look at how chemistry fits into the bigger picture of biology and why we really need a strong understanding of atoms and molecules and compounds in order to put together the different systems that we see in biology. So chemistry is just the study of the composition, properties, and behavior of matter. And as we can see from the diagram here, whether we're studying some biology, biochemistry, whether we're going to be looking at some environmental impacts, which we will in this class, education, pharmaceuticals, medicine, some of you may be interested in, it all goes back and has roots in chemistry, because everything that we look at, the building blocks of life, deal with chemistry and how those elements are held together, the bonding, and that's what we're going to start our discussion today with. So, if chemistry is the study of matter, what are the states of matter? So these are the forms that matter can take in the world around us. And these should be, I think, familiar with you already. But we start with solid, so ice, wood, concrete. And they have the lowest energy state. Then we go to liquid, which is middle in terms of energy. And then finally we've got the gas, which is the highest energy. So steam, vapor, clouds, all of those. And as the diagrams that we're going to look at will show you, they really do depend upon the amount of energy that each of them have. So when we look at the common states of matter, so you can see here the book is a solid, the water is a liquid, and the gas in a balloon. The thing I want you to focus on is look at the space between the molecules. So here in the gas, there's a lot of space in between here. That means there's a lot of energy. Those molecules are vibrating and moving fast and kind of forcing each other apart from each other. Look here in the middle, in the liquid, there is still some space, but there's less space now. And those molecules or those atoms are closer together. They're not vibrating as quickly as what we saw in the gas. And then finally, in the solid, you can see there's almost no space in between the atoms or the molecules. It's packed in very tightly. So they're not moving. It has less energy than the other two states of matter. So again, if we look at energy, which can be the same as kind of temperature that we see over here on the y-axis in the top graph here. And as we go through over time, as we add temperature, add energy to thing, we start with a solid. So in this case, it might be easy to think of as ice. So that's solid water. And at low temperatures, the molecules are close together and it stays at a solid. It's not until we reach the melting point of water that it starts to melt and we get the liquid and water in here. And the same thing, the temperature then rises as more energy is added and excuse me, then we reach the boiling point, at what point it will be turned to a gas or vapor. So we can see the three states of matter and the transitions that it takes, all due to the energy of the system. And the bottom graph shows the similar thing, where we can see to the left the blue arrow, heat being released as we go from water vapor to liquid water to solid water. Energy is released. And if we go in the opposite direction, when heat is being absorbed or added, we go from we go from ice to liquid water to water vapor. So the nature of matter is anything that has mass and takes up space. That's what matter is. And what's going to concern us are the elements. So there are 92 naturally occurring elements, and the good news for you in biology, there's really only 4 of them that make up organic matter. Carbon, hydrogen, nitrogen, and oxygen make up over 90% of organic body weight. So that's you, a moose, a worm, a flower, all those things. Carbon, hydrogen, nitrogen, and oxygen make up well over 90% of all of those. So those are the 4 main ones that we'll have to deal with. So now let's get into the actual chemistry of it. So an atom is the smallest unit of matter unique to a particular element. So think of some elements off the top of your head. It's probably pretty easy. There's things like gold, carbon, oxygen, hydrogen. Those are all elements, and they each have unique properties due to the composition of their nucleus and electrons. So within the atom, there are subatomic particles, and the three that we need to concern ourselves with are neutrons, protons, and electrons. So in the nucleus of an atom, we have neutrons, which are neutral, they have no charge, and protons, which have a positive charge. Then circling the nucleus in the electron cloud or the electron shells are the electrons, and they have a negative charge. So if we look at the diagram here, which I'll expand and make a little bit bigger, if we look at the diagram here, we can see that in the middle, the red and yellow, we have the neutrons in yellow and the protons in red that make up the nucleus, and then in shells around the outside, we've got the electrons that are negative. So ignoring the neutrons for a second because they have no charge, as long as the electrons and protons are equal in number, that atom is going to be neutral. And most of the atoms that we're going to be looking at, especially at the beginning, are going to be neutral, which means that the number of protons is equal to the number of electrons. So I'll make that a little bit smaller again, and we can go back to that. So here's a quick graph, and of this, what you guys really need to know at this point is the relative charge. So you need to remember that a proton has a charge of +1, a neutron has no charge, and an electron has a charge of -1. The symbols you should be able to remember: P, N, and E with a minus showing that it's got a negative. And the relative mass right now is not too important, but I do want you to know that protons and neutrons are basically equal, and the mass of an electron right here is so incredibly small compared to the proton and neutron that when we get to atomic mass and talk about that, that's why we're going to be able to ignore electrons, because they're so small compared to the mass of the protons and neutrons. So now a molecule is two or more atoms held together by chemical bonds. So now if we take atoms and we start to group them together. So one of the simplest ones would be a molecule of hydrogen, which because of its chemical nature will bond to itself. The oxygen in the air that we breathe in is actually diatomic. It's in the form of O2, and that's a molecule. Okay, so it's two or more atoms held together with chemical bonds. A molecule can also be something like water. Okay, so that's two or more atoms. In this case, they happen to be different atoms, hydrogen and oxygen, but that is a molecule as well. Now, when we look at a compound, compound is a substance made of two or more different elements. So in the case of water, water is a molecule, but it's also a compound. Hydrogen and oxygen, on the other hand, are molecules because they're two or more atoms, but they are not compounds because they're not two or more different elements. So some other compounds that you might be familiar with are things like carbon dioxide, CO2, which is a molecule, but it's also a compound. Sulfuric acid, H2SO4, same thing. It is a molecule, but it's also a compound. Okay? So not all molecules, all molecules are compounds, but not all compounds are molecules. And here's a quick picture to show that. So here's our hydrogen molecule, so which is just two hydrogens bond together. So that is a molecule, but it is not a compound. Here is our oxygen. Here's O2. So again, it's a molecule, but not a compound. And the other three here, water, H2O, sulfuric acid, H2SO4, and down in the lower right here, this is glucose, which is C6H12O6. Those three are all compounds as well as molecules. So that's our kind of our introduction into chemistry, and that's where we'll kind of wrap it up for today. So as you get into this, I know it will seem confusing at some points, but you just kind of got to stick with it, and it will start to make sense as we put things together and get into a little bit more of the biology of it. So thank you again.